So this video is going to cover Poisson and binomial distributions using a car example. So first, before we get started with the example, I want you to know that both Poisson and binomial distributions are used to work with discrete variables. Discrete variables are like counting numbers, maybe 1, 2, 3, 4, up to infinity, and even negative infinity. However, if you're counting a discrete variable, like let's say chairs, you can't have 1.3 or 1.5 chairs. So it's only including the counting numbers. Then Poisson and binomial distributions describe the probability of an event of interest, and they are probability distributions. Now for our example, like I said, we're going to use cars, and the problem is an automatic camera records the number of cars running a red light at an intersection. And analysis of the data shows that on average, 15% of light changes record a car running a red light. And we're assuming that the data has a binomial distribution. So this is the problem setup. These are the actual questions. So what is the probability that in 20 light changes, there will be exactly 3 cars running a red light? And the second one is, what is the probability that in 20 light changes, again, there will be no more than 5 cars running the red light? So the first thing to notice here is that we have 20 light changes. So that is our sample. And then our x value is 3 in this case. And in this case, it says no more than 5 cars. So that can be 5. It can be 4, 3, 2, 1, 0, because we're referring to cars running a red light. Now, before we get into answering the question, let's look at why this is actually a binomial distribution based on the way the question was set up. These are the characteristics of a binomial distribution. The first one is that a binomial distribution is used when the sample consists of a fixed number of observations. In this case, our fixed observations are cars that ran a red light. So each one is individual. Then each observation is classified into one of 2 mutually exclusive and collectively exhaustive events. So a car can either have ran the red light or didn't run a red light. These are mutually exclusive and collectively exhaustive because there is no other option for the car outcome. It's either they ran the red light or they didn't. Next, the probability of an event being classified as an event of interest is constant from observation to observation. So the conditions do not change throughout the sample. So every car has the same probability of running a red light. Obviously, we're not considering other factors, such as maybe the age of the driver or something that would affect the probability of running the red light. We are assuming that every car has the same probability, and those conditions are not changing. Next and last, the value of any observation is independent of the value of any other observation. So every car is independent of one another. You're not going to use one data point to count 2 cars. Each car is its own event. All right, now that we know why this is a binomial distribution, let's use the formula for a binomial distribution to actually solve the problem. So what I did here was define my variables. So we're referring to the first problem right now, where they're asking, what is the probability that there will be exactly 3 cars running the red light? So our n here is our sample, and that's 20. Next is our probability, which is denoted by pi, and I converted that to a decimal. And then our x value is 3. We can take this complicated looking formula and plug in all of the values we have here. So it makes it look a lot easier. And I just want to do a note about this symbol here. This means combination. So if you're doing 20 exclamation point, you're doing 20 times 19 times 18 times 17 times 3 times 2 times 1. So the reason why this is used in probability is because it accounts for all the other events that could potentially happen in that sample space. So this allows for all those other events to be accounted for. Now you may be wondering, why in the world are we solving this by hand when there are so many other tools for us to use out there? Thank you for mentioning that. I wanted to show that this is actually the formula that is being computed in Excel, which is what we're going to use when we have the function binom dist. So whatever inputs are used for this function, which will be these, it is taking those inputs and putting it into this exact formula to give us the distribution. So let's go over to Excel and actually see how this is working. So now we're in the Excel sheet called Binomial, and this you can actually find on Sakai under your lessons and under files directory. So let's change the sample size to 20 as per the question, and let's change the probability of an event of interest to 0.15, which was our probability of seeing a car running a red light each time there was a red light occurring. So the mean here is 3 cars, and the most important part that we want to look at is the binomial probability tables. They're asking what is the probability that in 20 light changes there will be exactly 3 cars running a red light. So I'll highlight just the 3. That is what we're looking for. There is a 24.28% chance that there will be exactly 3 cars running a red light. And you'll notice I clicked on this formula and we have the binom dist, and our inputs are the same as what I wrote on the whiteboard. We have A17, which is 3, so that's our x value. Then we have B4, which is the sample size, and the probability of the event, which is B5. Then we can solve this next problem really easily. It's asking what's the probability that in 20 light changes there will be no more than 5 cars running the red light. So that includes 5 and everything less than 5. Let's make that blue. So now we can add up all of these probabilities and we'll get our answer. So it equals to the sum of all of these. And now you can say there's a 93.27% chance that we would see no more than 5 cars running the red light in a span of 20 light changes. In its next problem, we're going to compare the binomial distribution with Poisson using another bit of information about this automatic camera. So it says the automatic camera records the number of cars running a red light at an intersection, which we know, but new analysis of the data shows that 4 new cars run the red light every 30 minutes. So now the way that we're presenting our data has changed. So this makes it a Poisson distribution. And the questions that we can now answer based on our Poisson distribution is, what is the probability that exactly 2 cars run the red light within a 30-minute time period? And what is the probability that more than 5 cars run a red light within a 30-minute time period? And if you'll notice, this 30-minute time period is what we call the area of opportunity. And that's what separates the binomial from the Poisson. Poisson has an area of opportunity, which could be time, it could be an area of space. That's what makes it different. Now, same as the binomial distribution, we're going to go through each of the characteristics of Poisson and see why this is a Poisson distribution. So firstly, a Poisson distribution is used when you are counting the number of times an event happens in an area of opportunity. So again, here's that buzz phrase. And we're counting the amount of red lights run within a time frame. This one says 10 minutes, but for our question, it's really 30 minutes. And in this case, it was 4 red lights in 30 minutes. The second characteristic is that the probability that an event occurs in a given area of opportunity is the same for all areas of opportunity. So it's going to be the same 4 cars on average in every 30-minute time period. That doesn't mean that 4 cars are going to run the red light every 30 minutes, but it's going to culminate into an average for each of these areas of opportunity. then the number of events that occur in one area is independent of the number of events that occur in any other areas of opportunity. So the 4 cars or 3 or 5 cars that run a red light in the 30-minute time period does not overlap at all with the next time period. There's no overlap in each area of opportunity. Then the probability that 2 or more events will occur in an area of opportunity approaches 0 as those areas become smaller. So there would be X amount or X percent of cars running a red light in 10 minutes, but those amount of cars or that probability becomes less and less as you decrease the amount of time until you have a very small period of time where there is close to 0 chance of a car running a red light. So that turns that into a Poisson distribution based on these 4 characteristics. Let's actually answer the question now. Again, we have our formula for Poisson, and as you know, we're not going to calculate it by hand, but I want you to see the inputs. The input for lambda is 4, and the input for x is 2, because the number of times we see the car running a red light in the area of opportunity is 4, and then we're asking what is the probability that there are 2 cars in this area of opportunity. And here is our formula. Now let's pop to Excel. So the Excel table for Poisson is almost exactly the same as binomial, except here there is one input, and that's lambda. We're going to say that is 4 because there are 4 cars within the 30-minute time period. And this probability table tells you that if there are 4 cars that we counted in this area of opportunity, then this would be the probability of seeing this x value. So the question is, what is the probability of seeing 2 cars? Well, that would be this value right here. Here's the formula, or the function, Poisson, and then our x value is the input, and so is our lambda. So for the entire Excel sheet, the one input is 4, but for the function, there are 2 inputs, x and lambda. So we can say now that there is a 14.65% chance of seeing 2 cars run the red light within the 30-minute time period. Now for the second part of this question, it's asking for the probability that more than 5 cars run the red light. So that means 6 cars, 7 cars, 8, all the way up until however many cars. It's really infinity, but when we get to 16, 17, 18, and those numbers, it's just 0 probability anyway. So we can find the sum of these values by doing sum, and we're going to only include 6 and greater. And the answer to this question is there is a 21.49% chance that we will see more than 5 cars run the red light within the 30-minute time period. So this is how you use Excel to solve binomial and Poisson distributions.